In the previous session, we looked at the Carnot article that Carnot devised in order to examine the theoretical engine based upon the process of isothermal steps and adiabatic steps. We found that this engine produced the highest efficiency, gave us the greatest amount of work for the amount of heat energy put in. And it also led to an expression for that efficiency, which showed us that the efficiency could be calculated by 1 minus the cold temperature divided by the hot temperature. And this expression, if we were to look at that, we would be able to say, how can we maximize this efficiency? What are the possibilities? And one would be, of course, in order to get the efficiency to be equal to 1, which is 100%, we would either have to have the hot temperature become infinite, or the cold temperature become 0. And neither one of those can be achieved, and therefore we can never build an engine which would be 100% efficient. And these are the statements that underlie what's known as the Second Law of Thermodynamics. The best way to think about the Second Law of Thermodynamics is to think about, number one, the fact that conservation of energy might allow a process to occur for which you have never seen it occur. For instance, if you were to place a cup of hot water on a table and go away for an hour, and you came back later, what would you find? Well, you'd find that water has cooled, wouldn't you? In other words, heat energy has flowed from the warm cup of water to the cooler surrounding environments. And conservation of energy would show us that the amount of heat energy that left the water is exactly the same as the amount of heat energy that the surrounding room gained. Now, why is it that you don't come back and find that cup has actually gotten hotter, and that conservation of energy still would apply? That is, the cup gained heat energy exactly the amount that the room lost. In other words, the room cooled, but the cup got warmer. Doesn't the conservation of energy, the first law of thermodynamics, essentially allow for that? And the answer would be yes. It certainly does allow for it. So the fact that you never see that happen must mean there is something more fundamental about our universe that simply ensures that doesn't occur. And so we encompass the expressions relating to these sorts of things that you never see happening. We encompass those in the statement of the Second Law of Thermodynamics. And one of those statements is you can't build a machine that converts heat into work completely. And by that we mean that if you put heat into a heat engine, it will do work, and then you throw away exhaust heat, the remaining. And if we could have no heat left over to throw away, no energy lost, in other words, the exhaust temperature would be absolute 0. And therefore we know we can't reach absolute 0. That's another consequence. Can't reach absolute 0. Therefore we can't utilize all the heat energy that we have to do work, because we're already throwing away some heat energy that is at some temperature. So these are two statements that embody the concept of the Second Law of Thermodynamics, is you can't build a machine that does work strictly from heat with no exhaust, and the exhaust can't be at absolute 0. Another consequence is related to this next statement, which is what I said, that we always find that heat flows from hot to cold. That cup of hot water on the table always cools down. Heat flows out of the hot to the colder surrounding environment. Never the reverse. So we refer to these observations as the second law of thermodynamics, and we define a quantity known as entropy to enable us to calculate a term which relates to this second law of thermodynamics. The entropy, S, is calculated in units of joules per Kelvin, and the importance of entropy is the change, and that is, the change in entropy is calculated by dividing the heat change in a process by the temperature at which that process occurs, or isothermal processes. For example, we know that when we undergo a phase transformation from a solid to liquid or liquid to gas, that these phase transformations occur at fixed temperature. So here we have an example of ethyl alcohol, which has a boiling point of 78 degrees Celsius, so it vaporizes at 78 degrees Celsius. We know that there is an amount of heat needed to vaporize a gram or kilogram of any substance. In this case, the latent heat is 100,000 joules per kilogram of ethyl alcohol. And the question is, what is the entropy change when a quarter of a kilogram, or 250 grams, of ethyl alcohol vaporizes at 78 degrees Celsius? Well, we can calculate. The entropy change is defined as delta S is Q over T. The Q in this case is the heat energy added to this ethyl alcohol, calculated by the mass times the latent heat. Well, notice we get 25,000 joules of heat energy added to the ethyl alcohol at its boiling point, converted to Kelvin, 351 Kelvin. So we get a positive 71 joules per Kelvin of entropy change. Since the final state minus the initial state, which is what the change in entropy is defined as, is greater than zero, then this is a spontaneous process. In other words, this will happen. If that entropy calculation turned out to be negative, a decrease in entropy, then that would not be a spontaneous or natural process. So it is observed that all natural processes occur with an increase in entropy. That's a very important statement. All natural processes occur with an increase in entropy. You may find that a small area of a particular system will have a decrease in entropy, but the larger area will have an increase. Let's use for an example your kitchen. In your kitchen you have a refrigerator. A refrigerator is a mechanical device that decreases the entropy inside the refrigerator. In other words, cooling down the environment inside the refrigerator. However, the larger area of the kitchen has an increase in entropy because of the exhaust heat that is exhausted out into the kitchen as a result of this cooling down inside the refrigerator. And so looking at the combined refrigerator plus the kitchen, the increase in entropy of the kitchen is greater than the decrease in entropy inside the refrigerator, and so overall we have a net increase in entropy, or a delta S is positive. So entropy is a measure of the system's direction in which it will spontaneously go as a result of the conditions or process the system is being subjected to. And natural processes increase entropy. Another way to look at entropy is to look at the order versus disorder concept. All systems proceed spontaneously and naturally toward a direction of increasing disorder and not towards order. So the natural direction is to increase disorder. And the reason for that is because there are more available states for a disordered system, and it has to deal with the probability of, well, how many states are available in going one direction versus going another direction. And we'll take a look at an example of this in our further discussion of the Second Law of Thermodynamics.